Hi everyone. Hopefully you can hear me okay. So let's get started. Welcome to week 9. Week 9 we will be going over formal charges as well as VSEPR theory, a lot of Lewis structures, and a lot of molecular geometry. Actually just a little bit of molecular geometry towards the end. So let's get started today. Okay. Awesome. So the first one that we are going to be working with, actually before we get started with what we're working with, I'll tell you which ones we're going to be covering. We're going to be covering end of chapter 7, and these are questions 29, 32, 34, 44, 51, 52, 56, and 93. So if you want to check with the chemistry textbook that the questions are located, you can always go to that textbook. It's the free OpenStax Chemistry 2E, I believe. I could put it in the link if you ever want to know the textbook that I'm taking these problems from. But other than that, let's get started. So the first question we have is going to be 29. And it says, write the Lewis structures for the following. And so we have H2CO. So when writing Lewis structures, what I'm going to be doing throughout these problems is I'm going to be writing down which kind of atoms we're working with and how many of them there are. And then we can figure out how many valence electrons are in each of the atoms. And then we figure out how many total valence electrons that we're working with. And then we can start to see how many bonds and how many lone pairs of electrons these molecules will have, or possibly ions in the later future. So let's get started on that. So we have hydrogen, carbon, and oxygen here. So we have 2 of the hydrogen. Let's do this. Yeah. We have 2 of the hydrogen. So it's going to be 2 times how many ever valence electrons it has. And we have carbon, and we only have 1 of that, and oxygen, and we only have 1 of that. So for hydrogen, the valence electrons, it only has 1 valence electron. So we just multiply that by 1. Carbon has 4 valence electrons. So we write down a 4 here. And then oxygen has 6 valence electrons. And so 2 times 1 is 2. So 2 plus the 4 plus the 6 will have a total of 12 electrons. And so those are the amount of valence electrons that we're working with. So let's write down just what the atoms specifically have on their own. So what hydrogen looks like just alone as itself. Same with carbon and oxygen. And then we can kind of figure out where are these bonds going to go. So for hydrogen, it only has 1 valence electron, but we have 2 here. So I'm just going to write both of them separately. The carbon has 4. So I'm going to write that like that. And then oxygen has 6. So as we can already see, with the carbon and the oxygen, if these, let's write this in the highlighter. So this right here can share a bond with each of these carbons, like that. And for the oxygen, it looks like it could possibly have a double bond here, because there's 2 right here and 2 right here, so that could form a double bond. So let's just try to start to see subtracting how many electrons that would be for all of those bonds and see how many electrons we end up with and see if that ends up working out. So let's do that. So what I'm thinking so far, it'll look like this. 2 hydrogens will be for the carbon, and there might be a single or a double bond. I'm not sure yet, so let's subtract how many electrons that would take for those bonds. So for each single bond, there's 2 electrons that the atoms are going to be sharing. So that's 2, 4, 6 electrons here. So we have 6 electrons left over. And so since the carbon has 2, 4, 6 electrons that it is already sharing, it would have a lone pair here. And then since the oxygen only has 2 electrons that it's sharing, it needs 6. But this doesn't work out because we only have 6 valence electrons that we're working with here. And this would come up to 2, 4, 6, 8 electrons, so we don't have that much. So it turns out that we will need a double bond between the carbon and the oxygen. And it's always okay if your first idea doesn't work out. Just going through the process and making sure everything is nice and happy with its maximum amount of valence electrons that it can hold, 8 or sometimes more for the third column or the third row atoms. But for this case, let's do a double bond right here. And so carbon is satisfied because it has 2, 4, 6, 8, and it has 8 valence electrons, so it's nice and happy. And so let's minus one more bond, and so we'll have 4 electrons left over for this. And since oxygen only has 2 pairs, it has 4 electrons right now and needs 4 more. We have 4 left over, so the 4 will go right there. And this molecule is nice and happy because everything is satisfied. And hydrogen, since it only has 1 valence electron, it cannot hold any more than that because it's sharing, one hydrogen. One of its electrons for the hydrogen is sharing one of the electrons with the carbon. So that's nice and happy in each one of those hydrogen-carbon pairs. Okay, so that is the answer for 29B. Let's move on to 29D. So we're working with chlorine, nitrogen, and oxygen. So chlorine, nitrogen, and oxygen, these are the ones that we're working with. So chlorine has a valence electron number of 7, nitrogen has 5, and oxygen has 6. I know these off of the top of my head because I've worked with them a lot, but going back over the periodic table and just double checking, some of these aren't as familiar, like selenium. You may not know what that is. It's also 6 valence electrons just like oxygen, but going back to the periodic table just to check which column it is in will tell you how many valence electrons it'll have. Okay, so adding up all of these, we have 7 plus 5 plus 6. And so 7 plus 5 is 12. 12 plus 6 is 18. So we have 18 electrons to work with. And just as we did last time, let's write down what each atom will look like when it comes to its valence electrons, and then kind of see where the bonds will be created from that. Okay, so we have chlorine has 7, so 2, 4, 6, and 7. Nitrogen has 5, so 1, that's 3, and that's 5. And then we have oxygen, which has 6, 2, 4, 6. Okay, so just by looking at this, because chlorine only needs one more electron to be shared with to have 8, since it has 7 right now, the nitrogen has a singular one right there that I purposely drew so that we could see this better. It could form a single bond, sharing those 2 atoms with each other. And since the nitrogen has 4 left on the top and the right there, and oxygen has 2 right here, these could possibly share a double bond because it needs 2 more, the oxygen does, and the nitrogen also needs 2 more. So just by looking at that, we can kind of think where these bonds will go. So let's do some subtractions from our total, since it's 18. So let's write down, just like this, ClNO. And usually when it's spelled out like this, the ClNO, it's usually telling you this is the order that it's in, that it's aligned in, but sometimes it's not. So just be aware of that. So yeah, let's subtract the bonds that we're thinking of. So I'm thinking let's just start out with 2 single bonds. So that's 2 times 2, since there's 2 electrons in each single bond that it's sharing. So that's 4. So minus 4 electrons. So that will have a total of 14 electrons. Actually, let's put it down here. So we have 14 electrons that we're working with here. So since nitrogen only has 4 that it's sharing, it would need 4 right here. And oxygen and chlorine each need 6. So let's do that here. Okay, so we had 14 electrons that we're working with, and this is the structure that it would be needed to satisfy that. But we may have gone over with the amount of electrons that we're working with, and so that's an indicator we need to start working with more bonds instead of lone pairs of electrons. So we have 2, 4, 6, 8, 10, 12, 14, 16, and we only have 14. So we're over by 2. So that's a good indicator that we need a bond to satisfy that. So minus 2 more. And since the chlorine already is satisfied with its single bond, we can't do another double bond because it's already satisfied with this single bond here, since it had 7 and now it's sharing 1 more. The oxygen, however, and the nitrogen can have another single bond. So subtracting 2 again, or 2 already, that will be 12 valence electrons left over. So let's see where that would be distributed. So the chlorine would have 6, since it already has 2 right here. So 2, 4, 6. The nitrogen needs 2, since it has 1, 2, 3 bonds, so that's 6 electrons, needs 2 more. And then the oxygen needs 4 more. So that's 2, 4. So 2, 4, 2, 4, 6, 8, 10, 12. And we had 12 valence electrons to work with, so it satisfies everything. So we are done for drawing out this Lewis structure. So that is what that looks like. Okay, let's move on to 29I. So this one, it's HCCH. So let's look at what types of species that we have here. We only have hydrogen and carbon, so let's write that down. So we have hydrogen and carbon, and it looks like we have 2 of each. So hydrogen times 2. So the hydrogen has 1 valence electron, just as we've done before, as well as the carbon has 4. So 2 times 1 is 2, 2 times 4 is 8, so it looks like we're working with 10 valence electrons. So again, let's look at what hydrogen and carbon look like just on its own. So this is what that looks like for hydrogen. Alright, let's put it on this side here. Try to imagine where this would bond before even starting with the final Lewis structure can help. That's what I'm trying to convey here. It's always just kind of picturing where things could be at and making a rough draft before being solidified, because there's a lot of different ways you have to go back in certain areas when you've overdone it like we've done. Used too many valence electrons that we didn't have. So those are the 2 hydrogens, and we have 2 carbons that we're working with, so that could go right here. We're working with 2, 4. Okay. So those are the atoms itself. So just by looking at this, hydrogen, it can only bond with one other thing, and it would be easier for it to bond with the carbon each than rather than itself. That's what I'm thinking so far. So if it were to bond like this, with the carbon next to it and then the hydrogens on the outside to each carbon, that could work nicely, because carbon and carbon, it likes to be like that. So yeah, let's see how many valence electrons this will need. So we have 3 single bonds so far. So that's 6 valence electrons. So that would be 4 valence electrons left over. But it doesn't look like that would satisfy it, because the carbon each has 4 valence electrons. So each carbon needs 4 more, and we need 8 more. So that's an indicator that we need 8 electrons to satisfy what this is at right now, but we only have 4. So we need to add more bonds. So since the hydrogen and the carbon can only have 1 single bond each, we would have to add more bonds to the carbon and the carbon. And so since we have 4 valence electrons, but we need 8, that's a good indicator that it's not just a double bond, this might be a triple bond. But let's just do double bond for now and see what that looks like. So if we did a double bond here, that would be minus, let's see how much that would be. So it would be minus 2 valence electrons. so that'd be 2 valence electrons left over, but the carbon and the carbon has 6 that it's sharing, so each need 2, so we would need 4 valence electrons, but we only have 2. So let's add one more bond, and the maximum can only be a triple bond. So if it had a triple bond, minus 2 more valence electrons, we would need no more lone pairs of valence electrons. And it looks like this is already satisfied. And it works out because the carbon each have 4 bonds with it, and so that's 8 valence electrons. And the hydrogens have 1 single bond, and that already satisfies it. So we are done with this structure. So that's what that looks like. Okay, let's move on to J. So we have chlorine, carbon, nitrogen. So chlorine has 7, carbon has 4, nitrogen has 5. So adding up all of those, we have a total of 16 valence electrons. So again, let's write down what that looks like. So we have 7 here, as well as carbon, 4, and then we have nitrogen, which has 5. Oopsie. So that's what that looks like. So just by looking at this, the nitrogen could bond with the carbon because of this single or this double bond here that could possibly work out. And this, since it only needs 1, it could bond with the carbon with one of its valence electrons. So let's see what that would look like and just make a mock of this. So we have, chlorine here. Chlorine, and then carbon, and then nitrogen. So we have 2 single bonds here, so that's 4 valence electrons. So that'd be 12 valence electrons left over. But it seems like we would need more than that because chlorine would need 6, carbon would need 4, so that's 10, and this would need 6. So that would be 16 valence electrons. We only have 12, so we need to put some more bonds here. And so chlorine and carbon is already satisfied with this because chlorine it just needed 1 bond with because it had 7 valence electrons. It only needed to share 2. So it looks like we could make a double bond between the carbon and the nitrogen. So let's minus 2. So that would equal 10. And so let's distribute, or let's think about if that would work. So if 10 valence electrons that we would have here. This would have 6 that we would need of electrons. This would need 2, and this would need 4. 2 plus 4 is 6. 6 plus 6 is 12. We only have 10. So it looks like we need 1 more bond. So that's minus 2. And so that's 8 valence electrons. So if we add 1 more bond, carbon is already satisfied since it has 8 there. And then for the nitrogen, it would need 2. The chlorine would need 6. And so let's count up what that would look like. So that's 2, 4, 6, 8. So that's 8 valence electrons. And that's exactly what we had. So that is the final structure of this molecule, or Lewis structure. So everything is nice and happy and satisfied. So yeah, let's move on to the next question. Okay, it's also a Lewis structure if you haven't noticed the pattern yet. Yeah, write the Lewis structures for the following, and this is a phosphate ion. So the only difference that right now is that we're working with ions instead of neutrally charged molecules. So since this has a charge, we will just add more electrons to our total amount of valence electrons that we're working with. So this is what that will look like. So we have phosphorus and we have oxygen. And so it looks like we have 1 of the phosphorus, and phosphorus has a valence electron number of 5. Oxygen has 6, but there's 4 of them. And so that's 24 when we multiply it out, and that's 5 up top. But since we have a 3 minus charge, we'll add 3 more electrons. Since it's 3 minus, it means there's more of a negative charge. That means more more electrons. So we add 3. So adding up all these together, 5 plus 24 is 29. 29 plus 3 is, what is that? 32. So 32 valence electrons. And so just as before, let's see what each of these atoms will look like, just their Lewis structures alone. So the phosphorus has 5. So 5 here. The oxygen has 6. And there's 4 of the oxygen. And so since the phosphorus is located first, it's a good indicator that all these oxygens are going to be bonded to the phosphorus. So it will look like this. Since there's 4 of the oxygen, there's 4 of them here. And so that's what that could look like starting out with. But we'll see how many bonds we'll need. So right now we drew 4 single bonds. So that's 4 times 2 is 8. So minus 8 electrons. That will be 24 left over. And so since we have 4 oxygens that we are working with, if you were to divide the 24 by 4, we would have 6 valence electrons each. Now this is what you would automatically assume, but when we're going to be calculating and starting to get into formal charges later, you'll see that since the oxygen will have a formal charge of -1 and phosphorus will have +1, it's an indicator that there's going to be a double bond needed. So you can always check with formal charges to see if your formal charges are leading towards a value of 0. And we'll get into that later, but just for now, we are able to add one more double bond to this structure. So if we added one double bond to this, since phosphorus can hold more than 8 valence electrons, this is still satisfied. So let's see what that would look like. So minus 2 more electrons, so we'll have 22 electrons to share. So the oxygen here will need 4, and the rest will need 6 each. So yeah, that is the total of 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and 22. So that satisfies 22 valence electrons that we're working with. Whenever we have phosphorus or something like that in the third column or the third row, right here, these ones can carry more than 8. So just for your own knowledge sake, you might have something a little bit different than the rest. So don't automatically assume everything is going to have 8. It's good to double check where these are located. Okay, so that is satisfied here, and let's put brackets around it. And since this is an ion and it has a charge of 3-, we're going to put the 3- on the outside here. Okay, let's move on to the next one. So we have iodine and chlorine. So this is iodine chloride, I believe. Oh, but this is not a, sorry, that's not ionic, so that's not the name of it. That would be ionic naming. Yeah, let's get started. So we have 4 of the chlorine, we have 1 of the iodine. So chlorine has a valence electron number of 7, and so does iodine actually. So adding up all of those, oh, and don't forget the charge. So this has a minus charge, so we'll add 1 more electron. And so adding up all of those, 4 times 7 is 28. 28 plus 7 plus 1, we'll have a total of 36 electrons. So those are the number that we're working with. Just as before, the iodine is located first, so it's going to be in the center, and the 4 chlorine are going to bond to it. Yeah, so let's write that down. And we don't need to write down what each of these singular ones look like here, because we know that the chlorine will all bond to the iodine, and so we don't really need to see what each of them look like, because that's really helpful if it doesn't all go to one thing. If it's in a row and you don't know which one will bond to what, that's what that's good for when writing down each of the atoms' Lewis structure. But for this, since we know, we don't necessarily need to do that. So since we have 4 chlorine here, I'm just starting off with 4 bonds. And so let's subtract 4 bonds here. And just to check, iodine is located right here. So it might have, I believe iodine has the ability to hold more than 8. It's always good to double check, like I said in the last problem. So iodine can hold more than 8, so just know that. Okay, so let's subtract 4 bonds, and 4 times 2 is 8, so minus 8. So 36 minus 8 will be 28 valence electrons. And so distributing amongst everything, chlorine will need 6 each. And so 6 times 4 is 24. And so let's put down those 24 first. So it's 24. Minus 24, and we'll need 4 valence electrons left over. But this structure, the iodine can actually hold more than 8. In this case, it's holding 12, so the 4 valence electrons go to the iodine. So that is what that structure looks like, and don't forget the minus sign. Okay, let's move on to the next problem. We're working with sulfur, oxygen, this is sulfate, I believe, and just as I said before, the sulfur is a part of the column that can hold more than 8 electrons as well, so just keep that fact for later. So we have 1 sulfur that we're working with, and then we have 3 oxygens, so 3 times 6, since it has 6 valence electrons, and sulfur has 6 as well. So, and then adding the 2 minus, so 2 minus, that's plus 2 more electrons. So adding up all of those together will be a total of 26 valence electrons. So let's start writing out what this Lewis structure could look like. So sulfur is located first. We have 3 oxygens, so it's safe to assume that the sulfur will be in the center. So we have each oxygen surrounding it. So right now we have 3 single bonds, so just starting out. So 3 times 2 is 6, so minus 6. That would be 20 valence electrons. And so each oxygen will need 6 more, so 6 times, I believe, 6 times 2, or 6 times 3 is 18, so that would be 2 valence electrons left over. But actually for this ion, the sulfur can hold more valence electrons, so we can actually do more than just that. We can add double bonds to this. And so let's see if that still checks out. So sulfur, it can hold 2, 4, 6, 8, 10, 12. 12 valence electrons, just as iodine in the last one. So since it holds 12 valence electrons, let's see if that can satisfy how many that we're working with here. So we added 3 more, so minus 6. So that'll have 14, or what is that? Is that correct? That's 20 minus 6. I believe that's what that is. Should be 14 valence electrons left over. Okay, so since we have 14 valence electrons left over, and we have 3, that'll be 2 over here. So 4 each, since it's needing 4. So 4 times 3 is 12. So it looks like it'll actually need 2 more. Let me just double check that really quick on my answer key. I let's see here. I don't want to give out the wrong answer for you guys. Okay, so it looks like it might only carry only one of these because we have, so just to recap, we have 2, 4, 6, 8, 10, 12 that we're working with, and we have 14, but sulfur can't carry one more. So it looks like this might not be the structure that will be the final result. That's okay, it happens. So let's take one of these bonds off and see what that looks like. So we'll have a total of 2, 4, 6, 8, 2, 4, 6, 8, 12. So 12 valence electrons that we're working with. Or sorry, yeah, 12 valence electrons. So let's just start over here. So minus 12. And so that will be 14 valence electrons left over. And in each of these, this will need 4 of the double bonded ones, and this one will need 6. So if we add up all of these valence electrons, it should be 14. So that's 2, 4, 6, 8, 10, 12, 14. So now this is satisfied. It has everything that it needs for each of these pairs. So that is the answer for this one. So that is a 2- charge. Okay, let's move on to the next one here. So we have SbH3 for this Lewis structure. So let's write down what that looks like. So Sb has a valence electron number of 5. And the hydrogen, since there's 3 of them, we'll do 3 times 1. And these are all neutrally charged. So that is a total of 8 valence electrons. And so Sb, since it has 5 and hydrogen has 3, the Sb will be the center because each hydrogen can only, have one single bond. And let's see what this will look like for this kind of idea so far. So we have 3 bonds. So minus 6, since there's 2 in each. We'll have a total of 2 valence electrons left over, and so Sb needs 2 since it only has 6 valence electrons right now. So that satisfies everything. So that is the final answer for this one. It's very quick. Those are nice to have sometimes. Yeah, let's move on to B. So we have XeF2. And so Xe has a valence electron number of 8 since it is a noble gas. So it's already satisfied, but it can still bond with other things. And we also have fluorine, and we have 2 of that, and fluorine has a valence electron number of 7. So 14 plus 8, that will be 22 valence electrons. And so it's safe to assume that the Xe will be in the center, and the F, the fluorines, can surround it. So just with this kind of structure so far, we have 2 single bonds, so that'll be minus 4. So we're working with 18. And each of the fluorine will have 6 because it's already sharing 2. And so that will be 12 so far. And so since Xe can actually carry more than it can carry it can carry more than 8 valence electrons. So we can distribute the rest of the 6 to the Xe. So that will have 2, 4, 6 left over. So that's what that will look like. So it's 2, 4, 6, 8, 10, 12, 14, 16, 18. And we have 18, and so everything is satisfied. Awesome. So that is the answer for that molecular structure, or Lewis structure. So let's move on to 44, and now we are working with some of the molecules will have, so we're working with formal charges, so we'll have to look at the formal charges for different bonding, and that can really help with what these bonds will look like, because like I mentioned before, when you have two atoms that are bonded to each other and one has a -1 and one has a +1 formal charge, that's a good indicator that that'll share a double bond instead of a single bond to get those formal charges to a 0 value. And formal charges, that is the aim for everything, to have a 0 formal charge. If it's an ion, that's a different story. One of them has to have a charge, or the total has to be a charge of some kind to make that charge reality. Because when you add up all of the formal charges for every single individual atom, it should total what the overall molecule's charge to be. So if you have an ion of a -1 charge, if you add up all of the formal charges, it should equal -1. If it's neutral, all of them should equal 0. So that's just what we should know before proceeding. So the actual equation, I have it already up. So the formal charge equals the valence electrons of the atom minus the lone pairs that are surrounded the atom, that surround the atom, and as well as half the amount of the bonding electrons. So that is the equation. So we're working with selenium dioxide, and we have oxygen, selenium, and then oxygen. So since we have two oxygens, so it's 2 times 6, and we have one Se, and Se has a valence electron of 6, so we have 18 that we are working with. And so since we're working with 18, let's see what that will look like. We have selenium, that could go in the middle, oxygens can go on the outside. So we have 2 single bonds so far that we're starting with. And so that'll be 2, 4 electrons, so minus 4 electrons. And so that'll have 14 electrons left over. And selenium needs 4 here, and each of these oxygens needs 6. And so if you add up all those together, 6 plus 6 plus 4 will be, I believe that's 18. So that'll be 18 electrons. And we only have 14. So one of these bonds needs to be, it needs to have one more bond to satisfy that. So if we put the selenium on, or the selenium and the oxygen, one more bond on one side of things, let's see what that'll look like. So minus 2, so that'll be 12 valence electrons. So selenium only needs 2, oxygen needs 4, this one needs 6. 6 plus 2 is 8, plus 4 is 12. So we'll have 12 valence electrons that we're working with. And so that will work out. Awesome. So that's what that looks like for this one. Okay. So we have the structure so far. So now we can actually calculate the formal charge, because we need to know how many lone pairs and how many bonding electrons there are. So you always need to write down the Lewis structure beforehand. Yeah, so that is what the Lewis structure looks like. And so let's call this first oxygen, oxygen 1, and this one oxygen 2. So we'll have oxygen 1, oxygen 2. And we have selenium. So these are the 3 different atoms we are going to be calculating the formal charge for. So each of the oxygens, they have 6 valence electrons. Selenium has also 6. And so the first oxygen that we're working with, it looks like, for the next thing that we're calculating for is the lone pairs. So it looks like there's 2, 4, 6 lone pairs. So that's minus 6. And it looks like it has 2 bonding electrons, and we'll have to do minus 1/2 of 2 based on the equation. And so 6 minus 6 is 0, minus 1/2 of 2, that'll be -1 here. So this will have an overall formal charge of -1. And so looking at the next oxygen, this will have 4 lone pairs of electrons, so that's -4, and minus 1/2 of also 4 bonding electrons that it has. So it's minus 1/2 times 4. And so 6 minus 4 is 2, and 2 minus this right here, this will actually be 2 as well. So 2 minus 2 is 0. So this will have a formal charge of 0. And so looking at the selenium will have 2 lone pairs of valence electrons, and then 1/2 of the bonding pairs, it looks like it has 6. And so since it has 6, 6 will go right there. And so 6 minus 2 is 4, minus 1/2 times 6, that's 3. So this will have a formal charge of 1. And so if you add up all of these formal charges together, the ones right here, -1 plus 0 plus 1 equals 0. And since this molecule itself is neutrally charged, we know that we have calculated everything correctly because of the fact that the overall formal charge equals the charge of the molecule. Okay, so that is the answer for this one. Let's move on to the next question. So we're working with the formate ion, and it looks like it's left over of what I already have worked out. Okay, so this is what it has shown in the book. And at first, when I was working through these problems myself, I thought that this was correctly written, but it actually is not. So whatever the textbook gives you for the Lewis structures, sometimes it's not actually the correct way of writing it out. So let's actually work through if this is the correct Lewis structure for the formate ion. So it looks like we have 2 oxygens. So oxygen, so 2 times 6, and then we have carbon, and then we have hydrogen. And then we also have a minus charge, so let's add 1 more electron. So carbon has 4, hydrogen has 1. So adding up all of those, we have 12 plus 4 plus 1 plus 1, and so that'll be a total of 18 valence electrons. And so since we have 18 valence electrons, and we have 3 bonds shown on the very left here, that is minus 6 valence electrons, so that'll be a total of 12 valence electrons. And so if we distribute the 12 amongst everybody, it looks like this won't be satisfied, because if we put 6 here, because that's what each oxygen needs, that's 12 so far, but the carbon needs 2. So this is not actually the correct way of writing it. We'll need 1 more bond. So let's add 1 more bond. So if we minus 2 more electrons, we'll have 10 electrons to work with. And since the hydrogen can only carry 1 single bond, we will add 1 more bond to the carbon and the oxygen. So we will have the carbon to be satisfied since it has 8. And since we're working with 10 valence electrons, we'll put the valence electrons on the oxygens. So it's 2, 4, 6 that it needs. 2, 4, 6, 8, and 10, since the oxygen on the top there needs 4 more, since it's bonded with 4. So that is what the Lewis structure looks like for the formate ion. Yeah, and so always double check what it gives you. So that's what that looks like. So based on that, we can calculate the formal charges for everything. And so we'll label the oxygen on the top as oxygen 1 and oxygen 2. Okay, so we have oxygen 1, oxygen 2. And then we also have carbon as well as hydrogen. Okay, so based on the equation for oxygen 1, there is 6 valence electrons. So let's write down just all the valence electrons to work with here, 4 and then 1. Okay, so for the top one, the first oxygen number 1, it has, I believe, 4 lone pairs or lone electrons. So we'll write down 4. So minus 4 and then minus 1/2. And then minus 1/2 of the bonds that it's working with. So there's 4 that it's bonded with. So then minus 1/2 of 4. And so 6 minus 4 is 2. And 2 minus 1/2 times 4 is 2. So that'll be 0. So that is the formal charge of the first oxygen. And then for oxygen number 2, it has 6 lone pairs that it's working with. So minus 6, and then there's 2 bonded one that it is working with, so minus 1/2 times 2. And so 6 minus 6 is 0, and minus 1/2 times 2 is negative 1. So that is the formal charge of oxygen number 2. And for carbon, it looks like it doesn't have any lone pairs of electrons, so that is minus 0. And then it has 8 bonded electrons that it's sharing. So that's minus 1/2 times 8. And so 4 minus the 1/2 times 8, that'll be 0, since 1/2 times 8 is 4. So 4 minus 4 is 0. And for the hydrogen, there's no lone pairs of electrons, and there's only 2 that it's sharing, so 1/2 times 2. So that's also 0. So when we look at this, the total number of the formal charges, if you add up all of these individual ones together, it'll have a value of negative 1. And so it has a minus charge on the ion itself, so that works out, it checks out. So that is the final answer for all of these formal charges. So let's move on to see how many more that we're working with here. Let's move on to 93 first before we get to the other ones, because I want to go over electron pair geometry before doing more Lewis structures, so just so we have that covered for today. Okay, so 93, that's the one we're working on. So we have chlorine and then we have fluorine. And so the valence electron number of chlorine is 7, fluorine is also 7, and we have 5 of them, so 7 times 5 plus 7, and it's neutrally charged, so no need to add any more electrons. So that is a value of 42, I believe. Yes, 42 electrons. And so since chlorine is written first, it's a good indicator that that will be in the center. So let's write that down. So chlorine, and then we have fluorine, which there are 5 of them. There we go. Okay, so since those are distributed nicely, let's see how many bonds we had here. And oh, also chlorine, just like the other oddball atoms out there, it can hold more than the 8 electrons. It can actually hold, I believe we have 5 here. It can hold 12 valence electrons. So just so you know about that. So we have 42 that we're working with, and we've written 5 bonds, 5 single bonds. So 5 times 2 is 10. So it's minus 10. So we have 32 valence electrons that we're working with here. And each of these fluorine will need 6 because it only has 2 that it's bonded with. So 6 times the 5 will have a leftover of, or 6 times 5 is 30. So if you minus 30, it will have 2 valence electrons left over. So let's write down all of those 30 valence electrons. There we go. And so since there is 2 left over, like I said about chlorine, it can hold 12. So we'll add that lone pair to chlorine here. So that's what this one will look like, its structure. Awesome. And so this question is not only asking for the Lewis structure, what it's asking for is the electron pair geometry. So just by looking at this, when you're figuring out the electron pair geometry, you want to look at how many bonds it's connected to and how many lone pairs that it's connected to from the base one. So chlorine has 1, 2, 3, 4, 5 bonds, and it has 1 pair of lone electrons. So I have a PDF of the names for everything, but you'll end up needing to memorize or at least become familiar with a lot of the main ones. So we have 5 pairs as well as 1 pair of lone electrons. So it looks like this one right here, the square pyramid, it has 1, 2, 3, 4, 5 bonds, and then it has 1 lone pair of electrons. So the answer for this one will be square pyramid for its molecular geometry. So that is the answer for this one, square pyramid. So that is the answer. So let's move on to 93B. And we have chlorine oxide here, or chlorine and an oxygen, 2 of them. So we have 1 chlorine, and that has 7, and then we have 2 of the oxygen times 6, since oxygen has 6 valence electrons, and it has a minus charge here, so let's add 1 more. And so when we add up all of those together, that'll be a total of 20 valence electrons. And just as before, we can safe to assume the chlorine is going to be in the middle here, and the oxygens will be on surrounding the chlorine. And so let's start out with 2 single bonds to see what that will look like. So let's subtract 4, since there's 2 in each. So 2 times 2 is 4. And that'll be 16 valence electrons that we're working with. So the oxygen, each oxygen will need 6 to satisfy it. So that's 12 that we've written out so far, and the chlorine needs 4. So that also satisfies the chlorine. So we have 2, 4, 6, 8, 10, 12, 14, 16 valence electrons that we've used. So this structure is complete for what it'll look like. And it also has a minus charge, don't forget that. Okay, so for this chlorine, it has 2 single bonds and also has 2 pairs of lone electrons. So let's look at that sheet again. And so we have 2 pairs of the lone electrons, as well as it has 2 bonds. So it looks like it'll be a bent geometric shape because it has those 2 lone pairs and it has those 2 bonds. So it'll be bent. Or linear bent because it has the 2. Okay, let's move on to the next one. So we have selenium and we have fluorine. So selenium has a valence number of 6, fluorine has 7, and there's 4 of them. So adding up all of those together, we have a total of 34 valence electrons. So we have 34 that we're working with, and selenium is in the center. It's safe to assume that as well. And so let's work on the surrounding atoms. So we have 4 of those. So if we have 4 of the fluorine, so let's write those down. And so since there are 4 that we're working with, and there's 4 bonds that we've written, so that's 8 valence electrons. So minus 8 here. That will be a total of 26 valence electrons. And so since selenium, it can hold also more than 8 valence electrons, just so you know. If we put the 6 valence electrons on everything here, because that's what the fluorine needs since it already is bonded with 2. 6 times 4 is 24, and we have 2 valence electrons left over, and so the selenium will carry that as a result. Okay, and so let's look at our chart here. We have 4 bonds and we only have 1 single bond, or 1 lone pair. And so let's look at what that'll look like. So it looks like this one, the seahorse or seesaw, that is the one that we're looking for since it has 4 and has 1 single bond. So that is the answer for that one. We have seahorse or seesaw. Whichever one you like better. So that is the answer for that structure. And so this will be the last one that we'll be working on today. We won't have time to go over the other questions. But yeah, let's write this one out. So we have phosphorus, and then we have 2 hydrogen and also a minus charge. So we have phosphorus, hydrogen, and there's 2 of them. And then we have a charge. And so phosphorus has a valence electron number of 5. And there's times 1, so that's 2. So 2 plus 5 plus 1, that'll be a total of 8 valence electrons. And so the phosphorus can go in the middle. Hydrogens can surround it because each one has a single bond. And so because hydrogen can only carry a single bond between these, we can't actually put any more double or triple bonds that could possibly be there. So we are technically done with the bond form. So that's -4 since we've drawn 4 that have been bonded. So we have 4 left over, and the phosphorus needs 2 more pairs. So that is what that looks like for this structure. And it has a minus charge. And so since it has 2 bonded pairs and then 2 lone pairs, let's look at the sheet again to see what that'll look like. So it looks like it'll also be this one, the bent, with the other form or the other structure that we drew it for, the one over here. But yeah, it'll also be bent. A bent structure. Okay, so that is all I have for today. It seems like it's almost 1 o'clock. Thank you for watching. Hopefully this cleared up a lot of possible confusions on how to calculate formal structures, or formal charges, as well as Lewis structures and molecular geometry. Yeah, so tune in next week for more chemistry content. Let me know if you have any questions, and have a happy holidays, and I'll see you all next week.